Okay, here we'll solve a problem with a harmonic oscillator. We will have the following second order equation. The second derivative of y with respect to time plus 6, the first derivative of y with respect to time, plus 8y is equal to 0. And this is a harmonic oscillator problem because all of the coefficients here, the hidden 1 here, the 6 here, and the 8 here are all positive coefficients. Okay, so let's figure out what sort of damping situation we have going on here. Let's look at b squared minus 4ac. That is going to be equal to b squared is 36 minus 4ac in this instance is 32 because 8 times 4 times 1 is 32. And we get 4, and this is a positive number. And when we have a positive b squared minus 4ac, this is called an overdamped system. So let's look at what the solutions are going to look like here. We need to solve this characteristic equation, lambda squared plus 6 lambda plus 8 is equal to 0. And we note that lambda plus 2 times lambda plus 4 is what this factors into. So we have 2 negative real eigenvalues, -2 and -4. Okay. Now, to get a picture of the phase portrait, between y and the velocity v, which is the derivative of y, we actually need to find the eigenvectors. Okay, we could write down a nice solution right now, but let's take a look at what's going on in the phase portrait. So to do that, we need to go back to our system that we would create. We would have that the derivative of y with respect to t is v, and the derivative of v with respect to t is equal to -8y minus 6v. Okay. So if we want to look at the eigenvalue lambda equals -4, that would correspond to -4y is equal to v, and -4v is equal to -8y minus 6v. And now we need to find a pair y and v which works. This is not unique as always, so just pick y equal to 1, and then v is equal to -4. So there's our eigenvector associated with the eigenvalue. And for lambda equals -2, we do a similar calculation. -2y is equal to v, and -2v is equal to -8y minus 6v. But again, we can only pay attention to the first one if we want. We choose y to be 1, then v gets to be -2 from this equation right here. And so there is the eigenvector associated with lambda equals -2. So let's draw the phase portrait. Here is my y. Here is my v. And we had 2 eigenvalues. Lambda equals -4, went with the vector 1, -4, so that's a line of slope -4. And lambda equals -2 goes with the vector 1, -2. Okay, so let's draw these vectors here. So the -2 one will look something like this. This is for lambda equals -2. And the -4 one will be steeper, something like this. Lambda equals -4. Now along these lines, solutions that start on these lines stay on these lines, go towards the origin. Solutions that start somewhere else, however, go towards the origin in other ways. So solutions that start over here will kind of curve around and go towards the origin like that. Why do we go this way and not the other way? Well, that's because lambda equals -2 is the smaller negative eigenvalue. So the e to the -2t term is much larger than the e to the -4t term. So as time moves on, we're going to be looking more like e to the -2t and not e to the -4t, so we're going to be closer to this line of eigenvalues. In here, we get solutions that go like this. Here, we get solutions that look like this. And in here, solutions will go like this as well. So that's what the phase portrait would look like. If we wanted to plot y over time, let's pick this one right here. Here we note y doesn't change for a little while, but then it gets pulled towards the origin, like that. Okay? As I said before, this is overdamped because there are two separate eigenvalues.